This lecture will discuss about the variance of L1 regularized least squares. As we see that the L1 norm, the L1 penalty, or L1 regularization will promote sparsity in the solution. So in applications, we can introduce L1 to be used with another norm as a composite of different norms, so that it suits different purpose of promoting sparsity in the solution. So in this lecture, we will talk about three main problems, okay, called elastic net, group lasso, and fused lasso. So elastic net is going to be a combination of L1 and L2 norm. It will be used when there are some correlated variables in the regressor matrix. Okay, and in that case, the lasso or the L1 regularization doesn't perform well. So that's why we introduce another term, as we will see. For group lasso, it is an extension of L1 or the lasso, in the sense that now we would like to promote sparsity in as a group in a vector. For fused lasso, the sparsity is not actually promoted in the entries of X, but it is promoted in the difference vector of X. Okay, so as we see in the detail. Okay, so first let's talk about elastic net. Elastic net is basically a regression problem. Okay, the main cost objective is you want to minimize the two norm of the error, residual error. Suppose that you use linear model y hat equals ax. Of course, in the first objective, you try to make a model that gives a best approximation for y. But then also you have the penalty terms consisting of L2 and L1 norm. Okay, here you have the parameter 1 minus alpha and alpha, so it's a weight, okay, that you can vary. You can vary alpha. Of course, if alpha is large, you pay more attention to the L1 norm of X, which means that you try to have X tends to have smaller L1 norm relative to the L2 norm. And also you have gamma as a common as a penalty parameter common for both regularizations. Okay. When we look at this again, if I take a look at this as an optimization problem. Oh, it's freeze again. Let me. Whenever you notice that the screen doesn't move or anything, please let me know immediately. Because that means it freezes somehow. Okay. All right. I was just talking about varying alpha. If alpha is large, it means that you tend to have a smaller L1 norm in relative to the two norm, L2 norm terms. And then you have gamma as a common penalty parameter for the whole regularization. If you take a look at this as an optimization problem, of course, again, it falls into a convex optimization, because the L2 norm square, that is the quadratic function in X. You have this term, 2 norm square of X, that's another convex function in X. And then you have L1 norm, and as we saw from the lecture, any norm is a convex function. So the whole thing is a convex optimization constraint, unconstrained one. This combination is called elastic net. All right. If you put alpha equal to 0, of course, that reduces to the L2 norm regularization or the ridge. regression. On the other hand, if you put lambda equals 1, that reduces to the Lasso problem. Okay, so choosing alpha in the range of 0 to 1, that gives you a mix of the feature from L2 regularization and L1 regularization. Okay. Now I would like to mention that we have these results that we haven't shown you yet. There's a property can be shown mathematically that when you have a correlated variable, so think about matrix A that has n columns. Please be recalled that the meaning of each columns in A, okay, represent the predictors, all right, or the independent variables you use in the linear regression model. Okay, so if A1 and A2 are very correlated, or I mean, let's say if A1 and A2 correspond to two variables that are very correlated, it may be a measurement of some physical variable that are related to each other. Like they are multiple of one another. In that case, of course, the matrix A will not is not going to be full rank, right? If A2 is a multiple of A1. We have seen this before. This is called Co-Linearity Problem. Okay, Co-Linearity Problem. When you solve the least square, then these matrices may be not invertible. Okay, when some columns of A are dependent. But then we have this property that if you use rich regression or L2 regularization, in the case where collinearity occur, the corresponding coefficients x1 and x2 can be shown to be equal. That's a result from mathematical point of view. Okay. Then it means that if you use least square or if you use Lasso problem, then whenever you have collinearity problem, you will not see this kind of phenomenon. All right, that's why elastic net is proposed, so that you have a balance of sparsity of the solution, but also you can detect or observe when the regressor matrix has contains some correlated variables. Okay, this is still a strictly convex problem. For alpha is less than 1. Okay, and it will give you a unique solution if you have a strictly convex problem. Here's the example of the graph. We solve the elastic net problem by varying gamma. Gamma is a penalty parameter of this term. All right, and in this simulation, I intend to put the second and the first column of A to be highly correlated. Okay. As I said before, we have the results that if A1 and A2 are highly correlated, X1 and X2, the corresponding parameter, okay, will be equal. This is not obvious, but you can show in the rich estimate. Okay, so if we use the parameter X1 and X2 are labeled in this graph as the blue and the orange lines. So in this slide, you have X1, X2, the dot to X5, all right, in the graph. So you have 5 colors, 5 lines. So I plot the solution path of these 5 parameters as gamma varies. This is x1 and x2. It will be a little bit hard to know this, but you will see that as gamma increase to this point, all right, and if you use the elastic net that brings the feature of ridge regression and L1 and the lasso, you see that, okay, x1 and x2 will tend to be equal at a certain value of gamma. Okay. On the other hand, if you take a look at the lasso, the blue and the orange one, which correspond to the parameter x1 and x2, see, I mean, as you vary gamma, it doesn't look like these 2 parameters have, you know, some common values. Okay, both are eventually go to 0 because that's a feature of the lasso that brings sparsity to the solutions. So it means that using the lasso alone doesn't reflect the relative importance of 2 variables. Okay. Right? I mean, does it make sense? I mean, you have predictors A1 and A2 that are highly correlated. Okay, so you expect the coefficients to be equal or to be related in somehow. But using the lasso alone doesn't reveal that that information. Okay. So that is the elastic net. Let me mention that solving elastic net now is easy. They have command as well in MATLAB. So solve ridge regression, you know that you can have the closed form solution. For solving lasso and elastic nets, you can use I think you can use the lasso command or the elastic net command in MATLAB as well by specifying the values of alpha. Next, the second type, the second generalization of lasso is called group lasso. In this situation, suppose you have a vector x representing a parameter of your model. Now your vector x, if I draw x like this, x is a vector, but you partition x into blocks, 2 different blocks. Now you use k blocks, but each block is also a vector in Rn. Okay. So you have k blocks. Each of which is a vector in Rn. So the whole thing is a vector of n times k. It's a vector of size n times k. Now your purpose is not about having sparsity in x, but you want the whole block, okay, the whole block of x in some groups to be entirely 0. In this example, let's say you know that your x has 5 blocks, right? Somehow you know that some blocks should be sparse, but whenever it's sparse, the whole block is exactly 0. Okay, for lasso, if you use lasso, and of course, all right. So in each block, it contains sub entries of x, right? So for lasso means that if you use the regularization, it will bring some sparsity in the element in the entries of the element in the entries of x. But the 0 doesn't occur as a whole block. Okay. So how are we gonna promote this group sparsity? So we say we bring these, we bring each block of X by using the notation Xj. Now, Xj is not a notation of the J entry of X anymore. It means that it is the notation of X1, X2, X3, X4, X5. Okay, Xj is the jth block of X. You put two norm first. You put two norm of X first. That is a scalar. And then you take the sum of two norm over K blocks. And now you have the penalty parameter gamma. Okay. So in this, it means that what you do is, okay, you have a vector X that has different blocks. For each blocks, you compute the L2 norm. All right. So this is the L2 norm of the first block, L2 norms of the second block, and L2 norm of the K block. Okay. So if you have K blocks, all right, the whole vector is a vector in Rn times K. Now, this vector, the two norm of the vector K, the two norm of blocks in X, you concatenate them as another vector. This is going to be a vector of size K. All right. So then, if you use, I mean, if I call this guy a vector Z, for example, all right, what is the L1 norm of the vector Z? Sitipak?
Sum of two norm of xi.
Yes, right?
Yeah.
That's straightforward, right? And that's why this summation that we introduced in the course objective of the group Lasso is actually what it looks like, not looks like, it is actually the L1 norm of the vector that contains the two norm of all blocks of X. So when you, now the summation here plays a role of L1 norm. Okay, whenever gamma is big enough, of course, it's going to make the L1 norm, you can think of this as L1 norm of Z, all right? When gamma is big enough, the L1 norm of Z will be small. But when the L1 norm of Z is small, it means that it's going to introduce sparsity in Z. So the vector Z is sparse, but the entries of the vector Z is the L2 norm of blocks in X. So there's going to be some entries of I that Zi is 0, right? When we say that Z is sparse. So when some entries of Z's are 0, but you know that the norm, you know, any norm has a property that, okay, the norm is 0 whenever the vector Y itself is 0. So because Zi is the two norm of the block Xi, so Zi is 0 whenever Xi is 0, whenever the whole I block of X is 0. That's why the group Lasso can introduce the group of sparsity of vector in X. All right. So the group Lasso, of course, if n here equals to 1, which means each block of X is just simply a scalar, that reduces to the Lasso problem. Okay. From optimization point of view, this problem is still convex. I mean, the first term, obviously quadratic in X is convex. What about the second term? The second term, if you look at this, when you consider each block of X, that is affine transformation of X to, to Xj, right? If you map if you map the whole vector x into the jth block of x, that's affine transformation, because it means that you just multiply this vector to x to get xj. When you take the two norm is just a norm. I mean, two norm is a norm, of course, and any norm is a convex function. And a convex function of affine transformation, I mean, the composite of any convex function with affine is also a convex function. So that's why this term is convex. And then we use the property that the sum of convex function is convex. So that's why the whole thing is convex. And once you know that it's convex problem, then you can solve using like many software. Either it's a modeling software or the generic solver for convex optimization. But I also would like to mention that this is a non-smooth convex problem, which means that at some values of x, the co-subjective is not differentiable. This is from a result that we know that the function of two norm without the square, let me mention, without the square, this function is not differentiable at x equals 0, because the two norm is the square root of x transpose x, right? So if you take the gradient, you will get x divided by x transpose x, okay, or x divided by x, and that's the expression that, okay, that's not, I mean, it's only valid when x is non-zero, okay. There's a lot of story behind in terms of introducing algorithm to solve this kind of non-smooth problem, but okay, we will leave this stuff when we, take a look at this as from the optimization point of view. So let's see the result. So this is an example where x has 5 blocks. Each block is a vector of R4. What I do is, again, I solve the group Lasso problem as gamma varies. Okay. And now so when we see this, each column is a solution of x that can be viewed as 5 blocks. And then, as you see, when gamma varies, some blocks of x are entirely 0. And as gamma is large, the whole blocks become 0. Okay, so if I plot the term between gamma and the sum of two norm, so these represent sum of two norm in x, all right. So as gamma varies, the sum of two norm is decreasing to 0. That means, so whenever it hits 0, the whole blocks of x is 0. Okay. Solving group Lasso, you can use CVX as well. Okay, so you need to define, implement the code. Okay, just write the code to represent this term. The next one, and is the last one of generalization of the L1 least square, is called fused lasso. This is a problem that represent two terms of regularization. Okay, the first one is the simple the L1 norm term, and then you have the penalty parameter gamma 1. Now let's take a look at the second term. Okay, the second term, what you do is, of course, if you have x, a vector x, x1 until xn, now you do a mapping. You transform x using an affine such a way that you take the difference between consecutive entries. So what you do is subtract x1 from x2. subtract x2 from x3 and so on. So the last one would be xn minus 1. Okay. All right. So of course, when you do this, it's as I said, it's given by, you can take a look at this as a matrix transformation, F5 transformation, because it represents by by this matrix multiplication, right? So you're going to see minus 1 and 1, right? So this is called a difference matrix, the matrix D. Now, why are we interested in this vector? Let me call this guy as a vector Z. Okay. Suppose X represents your model parameter. And let's say if Xi represents model, sometimes can be used in this way. Sometimes you can use time varying model, time varying. So if you have time varying model, it means that your coefficients of the model can be varied with time. So let's say your Xi is a model parameter that represents at time t, at time I, right? So when you have x2 and x2 minus x1 or xi, or if you are interested in xi plus 1 minus xi, it means that you are observing the rate of change in the model parameter that are supposed to be varying with time. Okay, in the field Lasso, you have this purpose that you want to make z sparse. When you make the z sparse, it means that xi plus 1 xi, I mean in some entries of I, xi plus 1 minus xi is 0. So the meaning of this is that you want the parameter to have no change with the index I, and of course it depends on your application what index I would represent. If I say, oh, the index I represents the time index, it would mean that you want your parameter to be constant for some time indices. Okay, so with that purpose, you put the L1 norm of Z, because if your purpose is to put the sparsity in Z, but the sparsity in Z has the meaning that your original X has no change for some entries of I. Okay, so these block represent the L1 norm of Z. Okay, and the index J start from 2 to N. Okay, and now you have another penalty gamma 2. Okay. So by using, of course, you have two regularizations term. The pink term is called the fused Lasso term. The fused term, which means you fuse consecutive entries together, and the yellow term is the Lasso one. Okay. So the Lasso term represents the original purpose is that you want to make some entries of X to be 0. Okay, for the fused one, you want some consecutive entries of X to be equal. So this problem is called total variation denoising in the signal processings, where you may have, do I have the graph? Let's see. Okay, I have no graph. Okay, so for example, you have the signal that looks like this. Okay, but because of corrupted noise, all right, the blue one is the measurements. The orange one is the original signal you tend to transmit But when you transmit, the signal is corrupted by noise. Okay. Then, of course, when as a receiver, you want to recover the orange one, but what you observe is the blue one, right? Then what you do is you want to estimate x. Your x is the whole your x is the whole signal, which means what you want to do is you want to kind of clear all the noise, but because your original signal has the what, as I draw in this graph, your signal x seems to be piecewise constant, right? See, it's constant during some period, which means so if I represent the index I would represent the time. So during this period, it would mean that xi plus 1 equal xi. Okay, with that sense, when you formulate as a least square problem, you would tend to use the fused Lasso term, so that you introduce the sparsity in the difference of the solution. Okay, so this is one common problem in signal processing. Again, so when you vary gamma 2 and gamma 1, it depends on your purpose. If you want, the degree of the sparsity in x or the degree of the sparsity in the difference of x. Okay. And from optimization point of view, again, let me clear again. From optimization point of view, obviously the first term is convex because it's quadratic. The Lasso term is just L1 norm is convex. The last term again is convex because when you take a look at the term inside, that is the vector z, right? This term can be written as the L1 norm of the vector z, but the vector z equals dx. Z is a metric transformation of x, so z is a affine transformation. The L1 norm is convex, but it is the L1 norm of dx. So you can think of this as the norm function, which is convex, composite with affine. All right, so the result is still a convex function. Again, yet fused Lasso problem is convex. You can solve efficiently using the software. Now we take a look at the feature, the behavior of the solutions obtained from fused Lasso. In these two scenarios, I split into two cases. Gamma 1 is 0, gamma 1 is 2. Gamma 1 is the coefficient of the Lasso term. Okay. And then I vary. Hold on. This is supposed to be gamma 2, right? Okay. So I vary gamma 2 when I fix gamma 1. Okay. Gamma 1 is the penalty of the Lasso term. Gamma 2 is the penalty of the fused Lasso term. Okay. So you would expect that if I increase gamma 2, all right, I penalize more on the fused term, some entries of x would be equal. Now, when I zoom in, okay, so if you look at this graph, okay, this is again, my x has 10 entries. I have x1 until x10. So what I plot here is the solution path of the 10 parameters, the 10 variables. Okay. Okay. Which color do you see that the solution paths tend to be equal? Napat.
Sorry, again, please.
when you look at this solution path, all right, okay, please observe which pair of colors do you see that their solution paths tend to be equal?
Yeah, the orange one and the yellow.
Do you see yellow here? Which one is yellow? This is orange. All right, this is orange. This is red.
Oh, okay. Red and orange.
Red and orange, all right, tends to be equal as some values of gamma 2. Okay. What about another pair? Do you see another pair?
It's another red and purple.
Purple, red and purple at this point, right? Okay, very good. So as you see, as you vary gamma, you see that many pairs of variables becomes equal. And as you observe from this as well, but this in this picture is in the case of gamma 2 equals gamma 1 equals 2. Gamma 1 is a penalty of the Lasso term. It means that not only you want to make consecutive entries to be equal, but also you want individual variable to be 0, because that's a feature of Lasso term. Okay, so that's why in this picture, not only that you see that some pair becomes equal, you see that some variables here, okay, at this point, it becomes 0, right? When you see the solution part lies on the 0 value. Okay. So that would be, so these, in this video clip, I just explained 3 formulations. All of them are convex optimization. All of them are the variations of the L1 regularized least square. It means that each of them promotes sparsity in the solution in different ways. Okay.